right, guys, welcome. This is Anne-Marie Carrier from Herschel Jones, and we are starting our second official Google Hangout on air, and today we're going to be reviewing pure substances versus mixtures from our content this week on the Georgia Performance Standards. And I am going to go ahead and screen share with you, if that's okay, and we'll get started so that we can get through this and you guys can get a good night's rest. Okay. Okay, can everyone see the presentation?
Yeah.
Okay, thank you, Jalen. All right. So again, I had trouble allowing you to see it in full screen, so we'll do our best to get you to get it as big as possible. Okay, so here we go. All right. So, screen. All right. So first of all, the standard was trying to make sure that we could clearly identify the difference between pure substances and mixtures. Again, I feel like we kind of overkilled this week and really dove in. So we should know that elements and compounds are the only pure substances, right? Why don't you guys type in the chat box for me? Let me know if you feel like you understand this, like yes or no. How do you feel about this topic? Okay. Well, the second bullet here just reminds us that when we say they're pure, we're saying that they're only made of one kind of substance, that if you looked at it under the microscope, everything's going to be the same all the way through, versus something that's not pure would be made of multiple different types of materials, okay? So sometimes the stuff we're learning about, Cynthia, is just stuff that you have to commit to memory. That's why we kind of go over the vocabulary so that you can kind of memorize that and then learn it in context later as we're talking about stuff in class, okay? So feel free to ask any more questions. So we learned that we could find elements all over the world. We could own jewelry that was made of elements. We could build buildings from it. But what is the smallest amount of an element? You guys type it in the box or say it.
An atom?
Atoms, good. All right. So the biggest thing is, say you took a piece of iron, or you had hydrogen or oxygen or neon, okay, which you use in science. We could break it down to where it would be so small, it would be 1/1,000,000th of the size of a grain of sand, and all we'd have left is one atom. And that one single atom, guys, would have exactly the same properties, the same color, the same state of matter, the same boiling point, than the entire substance that you had when you had millions and trillions of atoms of that same substance. Now we know if we have a pure element, what's going to be the same about all of those? What's going to be the same about all of those atoms? If we have a pure element, they're all gonna be the same atoms, but they're going to have the same numbers of what?
Protons and electrons.
Right. What other things should probably be the same?
Neutrons.
Right, the neutrons. Now, Jalen, I think that was you, and the neutrons can sometimes change. If they change, what we would have is called an isotope of that substance. We hadn't really talked about that much. It's not on our test, but it's just an extension of what we're learning about. So it can have a different number of neutrons. It would still be the same element. It would just be fat or skinny if it were an isotope of the element. Okay, how about a compound? If we take more than one element and put it together, we know we can make a compound. Again, I use the analogy that, like compound words. Smallest amount of a compound is a what? What can you tell me, Cynthia? Can you type it or say it?
What?
The smallest amount of a compound? like water or salt. If we had the smallest amount of those, what would we have left? Begins with an M.
Oh.
Right, very good. The smallest amount of a compound's a molecule. So again, we know water is H2O, so it's made of hydrogen and oxygen, but those are atoms. And so hydrogen would have properties and oxygen would have properties, but if we put them together in a compound, they make a new substance with new properties. And I know I keep saying that it's hard to explain it at a basic level without getting into too much detail, and I don't want to confuse you any further. So the idea about these pure substances is that last bullet there, that if we start to break those things down further, we can only get to the smallest amount, an atom, or the smallest amount, a molecule, and still have those same properties, right? Because again, if we break a molecule of water down, all of a sudden we just have elements or atoms. We no longer have water. And then the same thing with gold. We can break it down so we have just one single atom of gold. It would be invisible. It'd be so small we couldn't see it, but it would still be yellow in color. It would still be kind of malleable, and it'd still be a metal, so we know that it would conduct electricity. Okay?
Okay.
All right, so we're going to look at these just real quick. I know last week we talked a little bit about atoms, but since your feedback from the poll everywhere, phone poll in class, indicated that we had some problems with the periodic table, I just want to go over this real quick, okay? So we know every type of atom that's known to man. It's a pure substance, but it's found on the periodic table. So it's the periodic table of what?
Atoms.
Element.
Elements.
Yeah, Jalen, good. The periodic table of elements. So every element has its own atomic structure, and so we know each atom has a different number of protons, neutrons, and electrons, okay? So I want to make sure, because, see, I know what the test looks like. What particles make up the mass of every atom? Let's see if, Joel, can you tell me? Joel Roche?
I don't. Is it particles?
Yeah, which two particles make up the mass of every atom? Think about the atomic mass, right? They call it the atomic mass on purpose because it's what two particles?
It's protons and electrons.
No, close. You're half right.
Protons and neutrons.
Protons and neutrons. Where are they found? Thank you, Emmanuel. I'm sure that was you. Where are those protons and neutrons found?
In the nucleus.
In the nucleus, right, guys? So the important part about atoms is for you guys to know the mass of the whole atom. We said it's really, really small. Like if you're looking at a piece of paper, it's the size of a dot on the piece of paper compared to the size of a whole football field. But even though it's really small, that's where all the particles are, because that's the protons and neutrons. So when we look on the periodic table and we see the atomic mass, we're saying 98, 99% of all the mass of every atom is right there in the nucleus. Okay, that's an important fact to know. And you need to know that the atomic mass is always protons plus neutrons. Okay, and again, that might be something that you just have to memorize, because I know we've said it a lot, okay? So if those parts take up the most mass, does anybody know which part takes up the most space? Think about the dot versus the football field, or we saw in that video it was the whole stadium, football stadium, right, compared to a marble. Which things took up the space of the whole stadium? Do you remember the TED video we watched comparing atoms, like what was the size of an atom?
I don't remember that.
No?
The nucleus?
Well, the nucleus has the most mass, but again, the nucleus is the marble, or the nucleus is the dot on your paper. So what's left?
The electron.
The electrons?
The electrons, right. The electrons are constantly in motion, and they're spinning around that nucleus. And because they're always in motion, you can't ever tell exactly where they're going to be, so they take up all this space. At some point in time, really, scientists can't determine where they're going to be within that space. They can just say, this is the size of the nucleus, and then the electrons are going to take up this much space around it. Of course, depending on what kind of atom we have, they might take up more or less space because some have more electrons than others, right?
Mm-hmm.
Okay. All right. So let's look at that atomic structure real quick. Here's a box from the periodic table. Can everybody see that?
Mm-hmm.
Okay, just want to make sure the screen is changing for you. All right. So we have the carbon box on the periodic table. Remember, the smaller number is always called the what, guys?
Atom?
Atomic number?
The
Atomic number. Good. And the atomic number is always the protons plus the electrons. So remember, it's funny because, or protons or electrons. But remember, they're usually the same in an atom because atoms are neutral, but they're not both in the nucleus, are they?
No.
No. So that's what kind of throws people, I think, sometimes. So one carbon atom is going to have 6 protons, and you can see in the picture at the top, they're located in the center, and protons have that positive charge, right? You'll need to make sure that you're familiar with those charges on the different particles. And then if it has 6 electrons that are surrounding it, taking up all the space, the math problem, again, would be +6 -6, so the overall charge of the atom is what?
Neutral.
Neutral. Very good. Okay? Now, do you remember how we figure out how many neutrons are in an atom?
You subtract the atomic number from the atomic mass.
Good. Was that Cynthia?
Yeah.
Awesome. Good job. That's exactly right. So if you can read the small print in that box, we take the big number, which represents the total number of particles in the nucleus in the center, and subtract the number at the top, which is the number of protons. So again, if the number at the bottom is protons plus plus neutrons, and the number at the top is protons, then 12 minus 6, the leftovers would have to be neutrons, okay? So this is where I was telling y'all that the mass of an atom is in the nucleus, because just think, that's what they put on every box on the periodic table, right? How many boxes are on that table?
180.
Awesome. 118 right now. So there's 118 different kinds of atoms. Every one has a different number of these particles. And so the pattern's going to be the same, okay? Now you see the symbol there for carbon?
Mm-hmm.
Mm-hmm. Big C for carbon or carrier, you know, the one, either one that's more important. Which one, are they all the first letter of the name of the element?
No.
No. Remember we talked about iron today, and it's Fe, and we talked about in one class that comes from the Latin root for the word, because all the elements weren't invented, or not invented, they weren't all discovered in the United States. So some of them have other terms that were used to describe them, and the person that discovered them was able to name them, okay? Plus, we have 118 elements, and we have only 26 letters in the alphabet. So just know it's not always the first letter of the name of the element, okay? Mm-hmm. Any questions about the atomic structure in the periodic table blocks, like here?
No, not really.
No, ma'am.
Okay, anyone else? Okay. I'll take your silence as that you are awesome and you understand it all.
Or
Yes? Or I can't see your faces because of the window, so all right. All right, so again, because you guys had indicated that you needed some help with the periodic table, we will be going over that more definitely next week. Okay, towards the end of the week, we're going to have a couple days of review, but I just wanted to ask you then, thinking about what you know about the periodic table, let's think about each of these comments and let's determine if it's true about the periodic table, okay? So you guys that have a text box in the group chat, can you just type yes or no for each one as we go, so that way everyone who is listening doesn't steal your answer? Well, I mean, I guess they could read your answer too, but I want you all to think about it, okay? So the first one, let me know if you think it's true or false. Elements increase from left to right in atomic mass. Think it's true or false? They increase from left to right in atomic mass. Okay. The first one on the left, the first element on the whole table, does anybody know what that is?
Hydrogen.
Hydrogen. Awesome. Hydrogen. Good job, Jolene. And so its atomic number is 1, and its atomic mass is actually only 1. It's the only element on the periodic table that has no neutron. It only has 1 proton and 1 electron. So its atomic mass is 1. As we read from left to right, not only do the atomic numbers increase, but their mass increases. Because again, where's the mass? It's the number of particles where?
In the nucleus.
In the nucleus. So if we're having more protons, then doesn't the mass have to increase too?
Yes.
Yeah. So as we go from left to right, just like we read a book, left to right it increases in atomic mass. Then we go to the second row and it gets even bigger. Then we go to the third row and it gets even bigger. So the biggest, fattest, massive elements, are they at the top or the bottom?
The bottom.
At the bottom. Good. So maybe that'll help you with the next one. Do you think elements decrease in number of protons as we go from bottom to top? True or false?
Yeah.
Elements decrease in number of protons as we go from bottom to top. Okay. Good job of just seeing if anybody else was going to jump in. That is right. Because, of course, if they increase in mass from top to bottom, that means they're going to decrease going from bottom to top. And see, I reversed it to see if I could trick you. So make sure on the test, you know, sometimes some of you guys are quickly trying to be the first one done, and you rush through your reading, and you miss little things like that, that it's going from bottom to top. And then that can help you, because I know you know this information, okay? So be careful to read, or be cautious to read carefully on your test. All right, how about letter C? Elements become more reactive as we move from left to right. Remember, reactive is like explosive, and let's see, tend to form compounds, bond, and become reactive and explosive.
Oh.
From left to right. It's okay to say not sure. Okay. Most of you got it. It is actually false. Okay, they're more reactive on the left-hand side. Remember, which family is the most explosive reactive?
The noble gases?
No, that's the most stable.
Alkali metals?
Alkali metals, good. The alkali metals, was that Colin?
It was Jolene.
Oh, okay, sorry. I'm having a hard time telling your voices without looking at you. So on the left-hand side of the periodic table, we have very reactive, explosive elements. That's why hydrogen's over there. Remember that those the properties, guys, are of an element. They are similar in a family, in a column. Do we remember why? What makes them act the same? Like each column. They're all similar because they have the same number of what?
Valence electron?
I'm back in.
Very good. That's it. Valence electrons. And that's the electrons in that outer shell. So that first column only has one valence electron, And that makes them freaky, makes them explosive, makes them very reactive, okay? So remember on the right, the noble gases, those are the elements everybody wants to be. They're very, very stable, okay? Because you wouldn't think you'd have like a crazy Queen of England, right? You wouldn't think the nobility, the people that the common people look up to, they're not crazy. People don't go, I want to be that crazy person. They want to be the stable people who got it down, right? Kind of agree?
Yeah.
Okay. So the crazy reactive, when you think of reactive, think of somebody that's very explosive, very reactive, like ready to blow, okay? Those are going to be on the left. As we go to the right, they're very, very stable. The noble gases have all of their valence electrons. They don't need any electrons. They're happy hanging out by themselves and being used in the world around us, okay? So that's, again, just a kind of a pattern that you need to become familiar with, and we'll go over the individual families next week. Are you guys asking me, did I miss something that I said that you want me to repeat? You said what? What is that?
I just came back and I missed a lot of things.
Colin was holding something, and it looked weird.
Oh, okay. All right.
I think it was his dog.
Emmanuel, we were talking about how the periodic table on the left, they're very reactive and explosive. The alkali metal families are the most reactive, but as you go to the right, they become more stable.
Okay.
Okay, so letter C is false.
Okay.
All right. Oh, and I got 2 Ds. So see, there's my first mistake of the night. No, I'm just kidding. It's probably my 10th. Okay, so the first letter D says elements in the same period have the same number of energy shells for their electrons. Do you think that's true or false?
True.
Okay, you got to type it in the box, Emmanuel. Okay, so let's think, what are periods? Remember, it's the periodic table. So who can tell us what periods are? Columns or rows?
Well, I think they're columns.
Well,
They're rows.
they're rows. Good. They're the rows side to side, and the columns are going to be groups. And the only way I can get you to remember that is that big houses have groups of columns. They're always 2 and 4 and 6. I've seriously never seen a house in my entire life with only 1 column on it. That would be, well, maybe if a half a house. Okay, so the periods are the rows. So that is true, and you guys seem to have gotten most of that right, that all the elements in the same row have the same number of energy shells for their electrons. So that just means, we talked about how they all have, can somebody mute their microphone? That we only have 2 elements in the first row because the first energy shell can only hold 2. Remember how we talked about you all have different strengths, so the energy shells or orbits for the orbits for the electrons are different strengths. So the first one's very, very weak. It can only hold on to 2. They would fly off of it or drop them if it tried to hold more. And then the second energy shell can hold 8, and the third one can hold 18. There's also some little sub-orbitals that you guys will learn about when you get to chemistry. But it's not important as long as you understand the pattern, is that the further down it goes, because they have more electrons, right, because the atomic number is increasing, they have to have more shells or orbits in order to hold them. Okay, does that make sense?
Mm-hmm.
Okay, glad you can't see me because I'm doing my little happy dance. Okay, y'all are awesome. Okay, the second letter D, the double D, is the elements increase in reactivity and energy as they go from top to bottom. What do you think? Are they more reactive at the top or at the bottom? Okay, well, let's, instead of talking about reactivity, let's talk about energy. Which particles are moving? Protons, neutrons, electrons.
Electrons.
The electrons, right? Which ones have the most electrons?
The ones at the bottom.
The ones at the bottom. So which ones would have the most energy?
The ones at the bottom.
The ones at the bottom. Yeah, because they have more electrons, and that's where all the energy's coming from. They're moving. Remember we talked about kinetic energy and motion? So the ones at the bottom have more electrons, so they're like more energetic. But that's not important. That is actually a, it is true, okay? And I'm probably going to change that on the test anyway, but I wanted to go over it because I've seen it before somewhere. Hint, hint. Okay. So let's go ahead and talk real quick about compounds, okay? Because again, we're at 8:30 and I don't want to keep you on that. So we talked about compounds a little bit already. Our test question is right now it's scheduled a week from Monday. So I think it's the 21st maybe. So next week is going to be Monday. Tomorrow I'm going to do some demonstrations for you. I've kind of gone through that, and we're going to do that and fill the room with smoke before we take our benchmark test. And then we're going to, on Monday, do a lab. And then we are going to have some review the rest of the week.
I have a question.
I'm sorry?
I have a question about the benchmark.
Yes, ma'am.
Is it everything that we've learned so far in the year?
No, not at all. It really is just seems to be about this unit, like atoms, compounds, and mixtures. So I think you guys really are going to do great. I looked at it and I was like, wow, this test is easier than the test you'll take a week from Monday. So, again, I will be happy to replace your lowest test grade with the benchmark score if you score higher on it. Okay? So I'll be watching for that.
So when is the benchmark?
Benchmark is tomorrow after I do my demonstrations.
Okay.
Okay?
Does the benchmark have stuff about the periodic table?
It may have had a couple boxes, but I'm really not supposed to discuss it. I don't think. I mean, you don't really. It's kind of measuring what you already know and making sure that I taught you the right stuff. Okay? So I wouldn't worry about it because it's only a grade if you do exceptionally well on it, and then it counts. It helps you. Okay? So I know I looked through it and I felt like you know everything that's in there, okay? All right, so let's look at compounds real quick. Again, just like a compound word is more than one put together that has new meaning, if we take two or more elements and bond them together, we come up with a compound. Now, we didn't really talk about the different kinds of bonds because it's not in our standards this year, but bonds are always formed between elements because the atoms are trying to give, take, or share electrons. And you know how we talked about those valence electrons and some are reactive and some are stable? That's why they come together. Otherwise, they would all be like the noble gases and hang out by themselves. So coming together in pairs makes them stronger. It's kind of like you guys, okay? You all are really intelligent about different things. So if you ever heard somebody say, oh, if we put our two heads together, we could accomplish twice as much. It's kind of the same idea. That these atoms, if we only had 118 different things in the world around us, the world really wouldn't be diverse. It wouldn't be as interesting. So they come together to make new stuff and to give us all the variety that we have in the world around us. But in order to do that, they have to share their electrons. So there's a reason for them to pair up. Okay? So what did you guys say again that the smallest amount of a compound is?
A molecule.
You got it, Emmanuel?
It starts with an M.
Yes, it does. All right. So now we can have a molecule in a compound like water or hydrogen peroxide, or at the bottom, the most common compounds are salt, sugar, water, and carbon dioxide. Now, we're talking right now about chemical reactions. So the reactions that we're saying, we can break those apart. Do y'all remember what kind of reaction that would be if we pull a compound apart? It's like dead bodies in the ground. Remember me telling you that?
Decomposing?
Huh?
Decomposition?
That's it. Decomposition. Things
I got it right.
Yeah, things break down over time, and a decomposition reaction.
What happened?
Looks like
Hello.
It's scary.
Ellen.
Miss Carrie's still on.
I didn't do it.
Where is she?
What just happened?
She put herself.
We lost our teacher.
I don't know.
How do we lose our teacher?
Miss Carrier, you're muted.
What do
Come
you
back.
mean?
For them, to everyone.
No.
Can you hear me now?
Yeah.
Yeah.
Okay. I don't know what happened.
Come back.
You can't hear me?
Yay, she's back. She's back.
Okay, can you hear me now?
Yeah.
Yeah.
Okay. I don't know what happened.
Alright, we're gonna give you a fanfare to welcome you back.
Nice monocle, Emmanuel. Okay, that's you guys take. All right. So I don't know what happened, but I was just trying to get out to get back in. So let me go ahead and pull that back up. Are we doing good?
Yes,
I'm glad to see everyone. Jolene hiding behind the sun.
I am gone now.
Okay. But I can still hear you. So we'll learn about sound waves in a few months, okay? And then we'll have this discussion about that.
I'm getting crushed by the waves.
Okay, different kind of wave, but we'll get to that. Okay, so let me go ahead and pull up the presentation one more time because we don't have much more. Start screen share. Okay, you can see it again?
Yes.
Okay. All right. So what I was saying is that we can take them apart. So I just don't want you to think that the only way to take atoms and elements are to put them together, because we can rearrange them in all different kinds of order. And that's what we're going to talk about next week, is the law of conservation of matter, of mass, chemical reaction, signs of a reaction, and then kind of do an overview, general review of everything. But I'm trying to add in a little of old stuff, okay? Right. So here again are our most common compounds. Again, they're the different atoms bonded together. So I want you to be familiar with seeing the diagrams. Again, the different colors of atoms represent different types of elements. Okay. So here, carbon dioxide, even though you don't have the formula, is 1 carbon here in the center and 2 oxygen on the side. Hydrogen peroxide, does anybody remember the formula for that?
H2O2.
Very good.
Yeah.
H2O2. So we have 2 hydrogen, or the green ones, because here's, oh no, all right. No, these are hydrogen, and these are oxygen, because here we had 2 oxygen here too. All right? All right, so mixtures. Remember we said we're going to talk about pure substances and mixtures. So we're done with pure substances. Let me go back. Any questions about pure substances before we move on?
I don't think so. Wait, how are compounds considered pure substances?
I'm sorry, I can't hear you over the typing.
How are compounds considered pure substances?
Okay, because all of these, okay, say you had a glass of water or a glass of hydrogen peroxide. Every part in the entire thing, everything throughout the entire container of hydrogen peroxide would be in this ratio, 2 hydrogen to 2 oxygen. There's never going to be a lone oxygen in there. So we're saying if everything's the same all the way through, then it's pure.
Okay.
Okay.
I understand that now.
Oxygen would mean that we have just oxygen and it's all the same. There's nothing else in our air supply. So like people who are sick and get an oxygen tank from the hospital and have to breathe that, there's no other gases in there to to interfere with their breathing. So that's why sometimes people that have unhealthy lungs or breathing problems, they might breathe a tank of oxygen to help them because their lungs don't have to struggle to separate the gases and only breathe in the oxygen and then send the other gases back out. Because we talked about that, okay, so we're talking about mixtures next, that our air supply is a mixture of lots of different gases. So I know I told one of the groups today, when we breathe that in, the job of our circulatory system is to take the oxygen and diffuse it into our blood. But I want y'all to think about this. We breathe in lots of gases. Our body just doesn't keep them. Sometimes we do get bad stuff. Those are the pollutants in the air around us. But when we breathe out, part of what we breathe out is the other stuff that we already breathed in. Did you know that?
Yeah.
Because sometimes when people say, oh, we breathe in oxygen and we breathe out carbon dioxide, we breathe in lots of stuff. The only thing that stays inside our lungs is the oxygen.
The risk of it,
We learn something every day.
Well, I sure hope that's not the only thing you learned today, but I'm glad I taught you something.
Do you have a joke about this or something, Miss Carrier?
I'll check my jokes for you.
Okay.
All right. I'll check them. Okay. So, let's see. Air, gases, lungs. Where do the other gases, what does that say? Where do they go?
Yeah, because you said, like, you take in many gases, but you
Okay,
only...
so your lungs are like air sacs, like balloons. And so when you breathe in, all of the air goes in your lungs and fills up the balloon. But you have these small capillaries in your lungs where they're very small blood vessels, okay? And the oxygen, it actually moves through the holes in the walls and the capillaries and goes into your bloodstream. The other gases still stay in your lungs, in the air sacs in your lungs, so when you breathe out, most of them come back out.
Okay.
You know what I'm saying? But what's happened is all of the oxygen that went into your blood, when it did that, it pulled out the carbon dioxide out of your blood. So when you breathe out, you also breathe out some extra carbon dioxide, which is a compound. Interesting? All right. I know you don't want to just talk about random stuff because I got plenty of that in my head. Let me know sometime if you want to share.
Okay.
All right. So, all right. So mixtures. We have a couple different types of mixtures. Again, mixtures are not a pure substance because if we looked at them closely, we'd be able to see that they're made of different types of atoms and molecules from a variety of substances. It can be a mixture of different types of atoms or mixtures of mixtures or a mixture of atoms and mixtures both. Okay, so we say they're a mixture because they're sharing space. Our air is in our atmosphere, in our rooms, in the classroom, in our homes, right? There's different gases in the air, so they're mixed. It's mixed types of gases. Sometimes we said we can see the different stuff, and sometimes we can't see the stuff. So if we can see the different pieces, is it homogeneous or heterogeneous?
Heterogeneous.
Hetero, good.
Heterogeneous.
If you can't see it, homogeneous.
Oh, homo. Oh, I was confused.
You got it. You got it. Okay. So here just are some quick pictures of the two different types of mixtures. Again, homogeneous. We have solutions are a type of homogeneous mixture. That means that we have one thing dissolved into something else, like your Kool-Aid, your sweet tea. Right here at the microscopic level, it's a mixture because different things are still exist in the water, but we can't see them. So, okay, these are little teeny atoms inside. NaCl, what is that?
Sodium chloride.
Sodium chloride, good. What do we call it?
Salt.
Salt, good. Good. So salt is sodium chloride. That's what this solution is, salt water solution. And then heterogeneous mixtures, we can always see the parts in a heterogeneous mixture, okay?
There goes Joel.
What was that?
There goes Joel.
Okay, so here is our heterogeneous mixture of oil and water. Sometimes, guys, just try to remember this, that they're called suspensions or colloids. Okay?
So, Miss Carrier,
Yes, sir.
would it like if it's a Sprite, would like the bubbles inside of it be counted like a heterogeneous mixture?
I really count that as a homogeneous mixture because I don't think you can really count the air. I will make sure that that is not on the test so we don't have that question for those of you that really try to get that detailed. Trying to look and see. I don't think that is given as a possible answer choice. It depends on how detailed you are. You know, like some people go, oh, let me think of a good example of that. Okay, people could go, I did really good on my test. And really good for one person might be an 81. And some of you go, what? You did really good. You got an 81. I got a 97. That's really good. So sometimes, most of the time scientifically we have the same definition, but if you look closely enough, sometimes scientifically we can separate things, break them apart, and say that's not exact. Okay? So it's to what degree of precision you want to break that down. And this is why. That was, sorry, was that Jalen? Did you ask about the soda?
Yes, you did.
Okay, I'm trying to think of whose voice it was. All right, so if you look in your soda, on the side of the can, there are like 8 ingredients in that soda. The only one you can see are the air bubbles because it's a different state of matter, right? You can't see anything else. So that's why typically we consider it a solution, because everything else is dissolved into the liquid. The heterogeneous suspension, usually the particles are going to be much bigger, and you can tell without a doubt that, hey, this stuff is made of different stuff. Okay?
Okay, now I understand.
All right, so let's look at these real quick. A solution, again, is always a solid or some type of material dissolved into something else. Okay? So here is our salt water solution from that last picture. And do y'all remember, what do we call the thing that does the dissolving?
The solvent?
Do the rest of you agree or disagree?
I really don't know.
Not sure.
I know it, but I just can't say it. I think it's solvent.
The thing that does the dissolving is the solvent, right?
Yay! I got it right.
So it's a universal solvent. Water is used for almost everything, and that dissolves anything you put in it, okay? So think about solvent dissolves stuff. And then the thing that is dissolved is called what?
Gone.
It's solvent.
It's not the solvent, but the
Dissolve?
I think it's one of your vocabulary words. That's why we're going over it.
Hold on, Google, come to me.
Yeah, that's the convenient part, huh? It's called the solute. The solute.
Ah, it says it right here. Solute.
Hang on.
Solutions are made of solvents and solutes. So let me share this with you. Okay, here is another picture. We have the solute many times.
Joel, you're making so much noise.
Thank you.
Sorry.
All right, so the solute is a lot of times a solid, but it doesn't have to be a solid. And then the solvent a lot of times can be a liquid, but sometimes other things. So again, a solution is going to be one thing dissolved into something else, so it looks the same all the way through. A solution is always, always, always a homogeneous mixture. You can't tell it's made of more than one thing, but it's a bunch of stuff mixed together. So on the bottom, I listed some examples. Air, that would be in our atmosphere. Carbonated beverages, so there's the answer to your question. We have carbon dioxide in our drinks, but we typically don't indicate that that's another substance or a heterogeneous mixture. The swimming pool. We talked about that we use chlorine in a pool to kill the bacteria. You can't tell that they put chemicals in there, but there's other stuff floating around in the H2O. Wine and vinegar both are mixtures of stuff, and they're both in water. So, you know, we kind of talked about this a little bit. We had talked about last week regular alcohol, and I meant rubbing alcohol, but then some of you referred to actual alcohol. Do you remember that?
Yeah, I think so.
And we were just talking about, were those, bless you, we were talking about were those compounds or mixtures. Rubbing alcohol is a compound, but alcohol like wine or beer is a mixture. And so it's a solution because they take different ingredients and dissolve it into water. Now, when you, different types of alcohols like wine or beer or whatever, they have different amount of alcohol in there. So that means that they have just a small amount, a percent of alcohol, then they have other ingredients to give it flavor, and then they have water. So there's still other stuff in there. It's not just alcohol, okay? So
It's usually about 20% alcohol, isn't it?
I think it varies a lot depending on what you're drinking. Because I really don't know a lot because I don't really drink. So only special occasions with my family. So I don't know. So I'm not reading a lot of bottles. I'm not familiar with that.
I think beer and wine have less alcohol than like rum and liquor.
Well, I know when we talk about when we get to the health and the life skills at the end of the year, we'll take a look at that and we'll investigate that a little bit more, Emmanuel. Because they compare like a whole beer would have the same amount of alcohol as a shot of liquor, but I don't know what the percent is. Because the beer has a lot of water in it, where the alcohol doesn't. Okay, let's keep going though, okay?
Okay.
So sugar and water, again, that could be like sweet tea. And then the last one I thought was interesting, it's called an amalgam. That is kind of like an alloy, a mixture of the things they put in your teeth, the fillings, when you get a cavity. So do you all have cavities?
No.
All the time.
Oh, you do? Okay.
That's
Well,
Cynthia, brush your teeth.
any more candy then. No more candy for you. I'm just kidding. All right. So our heterogeneous mixtures, we can always see the parts. We're saying that the things that make them up just have much bigger pieces. Again, homogeneous looks the same all the way through. Heterogeneous looks different every day, every way, hands down. So you can see from these pictures, right? So we have salad. Can you tell what this thing on the bottom is?
Pizza.
A taco sauce?
Not
pizza?
Yeah,
That's a pizza salad.
it's a salad pizza.
Yeah.
Okay, it's got all kinds of mess on it, but this is a
I think
pizza.
you just ruined pizza for me.
I'm sorry, Gavin. I'm sorry. We'll give you a little sad jumbo with you.
Sometimes I have to go to CC's Pizza just so I can try all the crazy combinations.
And now we shall laugh at
Cynthia, I feel for you. Haven't eaten dinner yet either.
Yeah.
Haven't eaten either. So
I'm supposed
I'm going to go get some Zaxby's when we're done. That's my treat.
you. Oh, yummy.
So
8 o'clock though.
all right. So we only have a couple slides left. Okay. So let's go back. How do you feel about mixtures?
Pretty good.
Good, I guess.
Good. Any questions about the different mixtures?
No.
Okie dokie. All right, so I have like 2 question slides and then a game for us to play, okay?
Ooh, I like games.
Good, I hope so. All right, so the following, these statements, A through E, they either apply to pure substances or mixtures, but not both. So I want you to think about, like we did before, true or false, which one is describing a pure substance and which one's describing a mixture. Okay, we're going to go one at a time. So the first one says it's made up of elements in fixed proportions. That's like a ratio. So would that be, you can type in the text box so that everybody gets their shot. Would that be a pure substance or a mixture? Okay, so we're kind of mixed on our answers. Okay, so if we have elements and they come together in a ratio, we're saying I got 2 of this and 3 of this, but the entire thing would be the same all the way through. Like if I had 2 carbon and 3 oxygen, and the whole cup was 2 carbon and 3 oxygen, and it's a fixed proportion, that means it's the same all the way through. So should that be a pure substance or a mixture?
A pure substance.
Pure substance. Okay, so maybe that's just worded poorly. Made up of elements. Let me add the word connected, because I know if I use the word bonded, you would know the answer. Does that make it more clear?
Yeah.
Did it change in front of you?
Yeah, kind of.
I don't know.
You don't know? Did my typing change?
Connected in, it still says fixed proportions. It says fixed proportions and or ratios.
Okay, but you can see the word connected now. Okay.
Yeah.
I just wanted to make sure it changed, because you're not looking at like an image file. Okay. All right, so then the next one, the parts can be readily separated by filtration, distillation. How about, oh no, we talked.
Magnets.
What's that?
Magnets can also be used for
Magnets, magnetism, a sieve, which was like a strainer, right?
Yeah.
So type in the box, would that be a pure substance or a mixture? Okay, very good. So it's a mixture, because the only way we can separate a pure substance is like an atom. We can't separate it unless we go through nuclear fusion or fission. That's a huge process. Thank you very much. And then the other way would be through a chemical reaction, right? We can separate a compound through a chemical reaction. So we're going to talk about that tomorrow. And I don't want to keep you up late, because I want to make sure all of you are there, because it's probably the best demonstration day of the year. Okay? All right, so let's look at the next one. It's very difficult to separate the components of the substance. Oh, I just gave you the answer. What would that be, everybody? A pure substance or mixture?
Mixture.
Mixture.
Letter C?
Atom.
No, it's just pure substance or mixture.
Mixture.
It's very difficult to separate the components.
If you try separating a pure substance like an atom, what happens?
Right, but it's the same.
Pure substance.
Pure substance, right. It's very difficult to separate a pure substance, because we have to go through a chemical reaction or nuclear fission or nuclear fusion. That's the only way. Okay? It takes a lot of energy to do that. If we had that pizza, if we had the salad, you know, I don't know about you guys, but every time I get a salad from somewhere, there's always something I got to pick out of it. So I can separate it with my hands, right? And as Will said, we can use magnetism if we dropped, for whatever reason, a pack of paper clips in our salad. I could get them out with a magnet if I had to.
That's
and
strange.
if I had like put too much, if I had sugar water, I could boil the sugar water and separate, and the water would all evaporate, and I'd have a bowl of sugar when I'm done. But I can't do that with a compound. All right, how about letter D? The elements or compounds are not in fixed proportions.
The
Which
elements
would that be, pure substance or mixtures?
Yum. And everyone loves Pizza Hut.
Very good. That's definitely a mixture, okay? Because that means we can have different amounts of all different kinds of stuff, different elements and different compounds, or different compounds mixed together, okay? And which one would we be able to see that it's made from different materials? Mixtures or pure
Mixtures.
substances?
Heterogeneous mixtures.
Right. Heterogeneous mixtures would be right. Thanks for giving everyone the answer.
I'm
So,
sorry. I forgot.
so yes, that it would not only be a regular mixture, it would be heterogeneous because you could see. You'd be like, oh yeah, this obviously, right? That we've talked about this. Everything in the room around you right now, everything in our classroom, they look different on the outside because they're made of different chemicals on the inside.
Yep.
And so all the stuff that makes them up makes them different. Right? And the only types of chemicals that everything in the universe are made of are the elements on the periodic table. So, all right. So let's see. We've got one more slide and then the game. So we talked about this a little bit. These are our pictures of pure substances or mixtures. And so let's see. Just type in your answer. You can see that they are labeled A, B, C, D, and E. So which picture represents a mixture of two different compounds? Which one do you think are two different compounds? I think E. Okay, you guys are right. Well, let's see. 1, 2, 3. What about C?
A, C, and E.
Yeah, A, C, and E, guys, right?
That's what I put.
So, although in A it looks like we have two atoms bonded to themselves, an element, another source, and then in C, maybe the answer is officially C from their website, because both of those substances in letter C are both made from different types of atoms, right?
Yes.
E looks like it could be
Mixtures and elements.
yeah, it's two different compounds, but each compound, if you see it, is made of the same types of atoms. That's why they're the same color, right?
Yes.
Okay, so let's look at letter B. Which particle picture represents a pure compound? Which letter would that be? Go ahead and type it, please.
What just happened?
Are you guys all seeing everybody's answers and voting?
No, I chose mine first. I
think
did it first.
I think it's B because it's like only one thing. It's like the same thing.
Right, but if we have the same thing and it's only one type of atom all the way through, would it be a compound? What's the smallest amount of a compound?
Element?
So it would be E.
Multiple elements hooked together would be
A mixture?
a compound. So like, I mean a molecule. So letter D is going to be the right answer. See how every one of them is exactly the same?
Yes.
Yeah.
And in letter B, those could all be atoms just all squished together.
Right. Oh, I'll be right back.
Okay? Y'all see that?
Mm-hmm.
Okay, how about, which says, letter C, which particle picture represents a mixture of an element and the compound?
And I'm back. Hello.
Which one would be an element and a compound?
A.
A.
Yes, A.
Joel.
Because then we see that we have the blue dots are the elements, and purple and yellow are the compound. Okay, so which one then is a pure element? Think about what you guys thought before. Which one is a pure element, meaning everything, all the atoms are the same all the way through?
B.
The blue?
B.
Yep. B.
Blue.
Yeah. Try to make sure to use the chat box, okay? All right. So it is letter B. Good. And again, they're all the same, every atom throughout the substance. And we know that's a pure substance. You can see it. We know letter D is a pure substance, right? Because all of them are exactly the same. So which one would be a mixture of two elements? Two elements, Cynthia. B is one.
Yeah.
All the same.
No.
Now we're looking for two. Letter D, Joel, is a compound, pure compound, because they're all the same molecules.
Okay.
All right, so we got a couple left.
B or B. Oh, goodbye, Jalen.
So again, when we look at an element, we're saying the atoms are all going to be the same in an element. This one's asking which ones are only two elements. So really, the only one that can have two colors, only two colors.
All right, we're looking at F.
Letter E.
Oh.
That monocle doesn't seem to work for you.
I'm kind of wearing like over my glasses.
Okay. All right. So letter E is going to be two elements, the yellow ones and the purple ones. So it's a mixture of two different elements. So say you put gold and silver in a bowl and you shake it up, they're not going to bond. It's just going to be a mixture of two different things. Okay? All right. Let's look. We got just a couple more and then our game. So which one would be water?
What would
would represent water?
D.
D, very good. Remember, what's the formula for water?
1 hydrogen and 2 oxygen.
Are you sure?
No, 2 hydrogen and 1 oxygen.
Right.
I'm smart.
Yeah. So that means that each molecule has to have 3 parts, right? And in this one, you can see. Oh, I'm pointing at the wrong screen.
So you need the glacier.
This one, they all have three atoms, okay? All right, last one. Which one would represent something dissolved in water? Which one could be something in the water? Something dissolved in the water.
B.
Again, think about what water looks like. Kind of like it belongs in Disneyland, right? You notice how a water molecule looks like it has ears?
Like Mickey Mouse.
Uh-huh. So which one looks like it
I have my Mickey Mouse right here. Hold on, guys. Let me show you.
No, D is the pure compound because there's
Mickey Mouse,
nothing else
right
in there, right? So which other picture resembles that with something else in it? Could be 2 different ones. A is a good answer, and C. Very good. A and C could both be something in water because those other things definitely look like they could be water molecules.
Mickey.
All right. So last one. I have a game for us. Are y'all ready to play?
Maybe.
Okay. Before we play our game, we have any questions?
No. Can I win this game?
Joel, can you see me through those goggles?
You're still there?
Okay, maybe he's not
Bring
listening.
it downstairs so you can have your ice cream downstairs.
Okay, yay, ice cream.
Don't.
All right, save me
don't
some.
Nobody needs to know. No, you can do
Yeah, I know she.
I'll take that.
All right.
Bye, mommy.
So I actually think I have to unscreen share or change screens or something like that. All right, we're still here, so I'm glad you're still there. And I'm going to put on the game. You ready?
Love it.
All right, so I'm going to need you to type in your answers into the chat box, and then the answer that's most used or most provided, then I'll take the majority answer to answer on the screen. Okay? All right. So here we go. Okay, I'll try to make it. All right. I don't think I can make it any bigger. Okay, here we go. All right, wow.
I'm back. There's a lot of background.
Oh, it's saying in this chemical equation, look, we went over these today. All right, sorry, one sec. I got to fix the screen so I can see your answers. Uh-oh. Uh-oh.
Uh-oh. Ice cream.
Okay, you back? Okay, I can't see your answers just the way that the screen is organized. So we'll make it work.
Okay.
Daniel, your house is too loud.
I know.
This is
I
a better
want to be upstairs, but my parents don't let me eat upstairs.
Okay, Emmanuel, you go first. A substance that contains only one kind of atom is called what?
An element.
Okay, let's see. Very good.
I'm smart.
Okay. How about Jolene? I know you're still with us, right? You still with us, guys?
No, Jolene left.
Okay. So, Cynthia, A, L, C, U, N, and O are all symbols for what?
D.
D, elements. Very good. That's right. All right. The fact that iron cannot be changed into a simpler form tells you that iron's what, Wesley? I can't hear you, hon.
D.
You guys speak up, please.
D.
As in boy?
No, D.
As in dog, okay. Very good. It's an element. All right. Ooh. So we talked about this only one time. This isn't my game. It says stainless steel is a mixture of. Do we want to use a hint?
I
know this.
Yeah.
Okay,
Let's use a
hint.
Iron and chrome.
Think about the color.
It's iron and chrome.
Is that Gavin?
Yes, it is.
Okay. I was going to give you the question anyway. So there you go. Good job. Okay. Let me see who we've got. All right. Jalen, how about this question for you? In the chemical equation, 2H2 plus O2 equals 2H2O, what's happening? Water is made, a compound is breaking into elements that make it, hydrogen and oxygen are made, water combines with oxygen.
Is it A?
Well, think about, again, is a compound breaking into the elements that make it?
No.
Are we starting with a compound?
Yeah. No. D?
That B as in boy or D as in dog?
D as in dog.
Okay. No. See, it says 2H2 plus O2. So we have two elements, right, coming together to form what?
Compound.
To form a compound. 2H2O. What's H2O?
Water.
Water. So it should have been this one. That's okay.
Oh,
Let's
I get it.
Let's try again.
Okay, I get it now.
Let's try.
Two of the hydrogen.
All right. All right, you can only change or add blank to balance a chemical equation. Let's see. Oh, who was that? Okay, Colin, we didn't do this in your class, so I'm going to give this to someone else. Okay, Emmanuel.
Yeah.
You know what it is?
You can change or add blank to balance the chemical equation. Would be D. D as in dog.
Yep, coefficients. Those are the big numbers. Oh, I'm clicking on the wrong screen. Coefficients is right. Very good.
Right.
Okay. Joel, stainless steel is a mixture of what?
Iron and
Come on.
calcium. D.
Oh, we just did it.
Mysterious.
Y'all tell them which one it is.
B.
Iron and chromium.
Iron and chromium. Okay.
What is
So,
chromium?
Colin, this one's
Chrome
yours.
is the shine stuff on cars.
Oh, okay.
Yeah.
Come on, bro.
Okay, let's finish the game. Let's see if we can get 1,000,000. All right, Colin, this one's yours. In the chemical equation, 2H2 plus O2 equals or yields 2H2O. What's happening? Water is made, hydrogen and oxygen are made, a compound is breaking into elements, water combines with oxygen.
A.
That is right. Very
We
good.
beat the one we missed last time. Yeah.
Okay, so Wesley, A, L, C, U, N, and O are all symbols for what?
Who's this for?
For Wesley. I'm going like through the line at the bottom.
I think you skipped Joel last time.
Which Joel?
Joel.
Oh, he just answered one
Okay.
for us.
Oh yeah.
Wesley, what do you think the answer is?
Can't even know.
What are the symbols on the periodic table and for what? Do you need a hint?
Yes.
Okay. If there are subscripts, it's a compound or a molecule. There's not a okay, so what it's saying is there's no subscript, so it's not those answers.
Element.
Okay, that's correct. Very good. All right, when salt is dissolved in water, Cynthia, a homogeneous mixture or solution is formed, a heterogeneous mixture forms, a compound is formed, a chemical reaction occurs. When salt is dissolved in water.
Okay.
You ever had to put salt in water before to gargle with it?
Yeah.
Did magic happen? Was there a chemical reaction?
Joel.
Not a big one.
Okay, when you go swimming in the ocean, is there magic in the ocean?
No.
No, so it's probably not D. Okay? Is salt in water a compound?
No.
It's a mixture then, right?
Uh,
So it has to be A or B. Does it
it's
look
A.
all the way through? Okay. So we can just break them down. Good job. When you have the test, if you're not sure about the answer, again, just try to eliminate the ones that you know are wrong. Think about, well, what do I know about this answer choice? And then you can start to break it down. All right, so who is next in our lineup? Gavin, a substance made of more than one kind of atom.
Compound.
Okay, very good. Okay, Jalen, which can be separated into simpler substances by a chemical change only? into simpler substances, meaning that you still have something when you break it apart.
Would it be? Oh, an element? Would it be an element?
Well, if we break up an element, we're going to still have a substance?
Oh, please don't be wrong. I just can't be wrong here. Oh!
All right. All right. Well, good job. I'm going to type the, I just typed the link for that game in the chat box. So if you decide that you want to open it and go play it some more, have fun with that. But I think you did a really good job, and we have gone over pure substances and mixtures, boy, more than any other time. So I think that we've got that standard down. How do you guys feel?
I think I got this really good.
Okay. Does anybody have any questions before we go for the night?
I'm fine.
Okay, so again, feel free to click that link on the right before I close out. Thank you so much for attending. I know, Wesley, you were not here last time, so thank you. You guys will earn extra credit for participating in our Hangouts, okay?
All right.
I'm gonna stop the broadcast, and then, Wesley, I'll be calling you back.
Okay.
All right, y'all have a good night. Thanks for coming.
All right, bye.
Goodbye.